Hi everyone, my name is Shua, and today I am presenting our paper, an exploratory study on multilingual quality estimation. So, what is quality estimation? Quality estimation is the task of predicting the quality of an automatically generated translation at test time, when no reference translation is available for comparison. Given a source sentence, we translate the sentence with a machine translation system. We then use a quality estimation system to directly determine the quality of the translated sentence given the source sentence. Quality estimation can be used in multiple ways. For example, we can use QE system to reduce post-editing effort. We can save time and reduce costs if we only send translated sentences that receive low QE score for human post-editing. We can also use quality estimation to hide bad translations from. I will now introduce common approaches used by the QE community. There are two common approaches. The glassbox approach extracts glassbox features from the empty system. For example, in the case of statistical machine translation, we can use lexical probability or language model probability. For neural machine translation, we can use the softmax probability and attention weights of tokens as features. The black box approach extracts black box features from both source and translated sentences. In the current QE approaches, black box features are learned representations extracted by fine-tuning pre-trained multilingual or cross-lingual sentence encoders such as BERT, XLMR, or LASER. Glassbox approach is potentially useful for low-resource or zero-shot scenarios as it does not require a large amount of label data for training. However, it does not perform as well as state-of-the-art supervised models. Therefore, QE is generally framed as supervised machine learning problem. Traditionally, QE has been addressed with language-specific models, where separate bilingual QE models were trained for different language pairs. This is mainly due to two reasons. First, the lack of publicly available training data makes it difficult to assess how well QE models generalize across languages. Previous work also assumes that the quality label distribution of linguistic features exhibit traits that are not shared across languages. This work challenges the assumption by exploring different approaches to multilingual quality estimation. This was made possible by the recent availability of a new multilingual QE dataset. I will now describe the black box QE models we propose an experiment with. Our baseline QE model is based on the XLMR large model, which is a transformer-based contextualized language model with 24 layers and 16 attention heads, and pre-trained on more than 2 terabytes of filtered common crowd data. Our QE model concatenates the source and target sentences, and then encode the joint sentences with XLMR. We then use a multi-layer perceptron to convert the first token into a quality estimation score. We explore two training strategies. The bilingual training strategy trains a separate QE model for every language pair, while the multilingual training strategy trains a single multilingual QE model for all language pairs, where the training data is pulled together without language identifier. As multitask learning has shown promising results in different NLP tasks, we want to explore whether having parameter sharing across languages is beneficial and to what degree having language-specific predictors can boost performance. We explore the simple multitask approach, where we concurrently optimize multiple QE-based models that use language-specific training strategy. To account for testing in zero-shot conditions, we also train a language-agnostic component, which receives training sample from every language. We refer to these models as MTLLA and MTLLS. At training time, we iterate through the MTLLS submodels in a round-robin fashion and alternate between training the MTL-LA submodel and training the chosen MTL-LS submodel. At test time, we can evaluate a test set with either the MTL-LA submodel or the MTL-LS submodel trained on the same language pair as the test set. I will now introduce the dataset we use in our experiments. We use the official data from the WMT 2020 QE share task, which contains sentences extracted from Wikipedia and Reddit. This dataset contains 7 language pairs and is divided into 3 categories. The high-resource English-German, English-Chinese, and English-Russian. The mid-resource Romanian English and Estonian English. And the low-resource Sinhala English and Nepali English. We want to emphasize that at the time of publication of this paper, the test set is not released publicly to participants. Therefore, we use the official dataset as our test set, and we create a new dataset from the official train set. The dataset was manually annotated for quality using a 0 to 100 scale using direct assessment. The figure on the right shows the distribution of DA scores for the different language pairs. Now, I will show the results on the multilingual dataset. The table below shows the Pearson correlation of predicted scores from different models with the annotated gold labels. Generally, both multilingual-based model and multitask learning QE models outperform the bilingual models. This is especially true for English-German, where the best base BL model performs at 0.39, while base ML and MTL-LA perform at 0.47, which is 20.5% relative improvement over the best BL model. Now, we take a look at the average Pearson correlations across all language pairs. The complete results table can be found in our paper. The left 2 columns show the language pairs used for training, and the right column shows the average Pearson correlation across all language pairs. The average score of base ML across all language pairs is 0.69, which is 4.5% better than the average of base BL models. Here, we provide analysis of our results. The previous results clearly show that multilingual models generally outperform bilingual models. We observe some base BL models in zero-shot settings can perform almost as well as models trained on labeled data. We hypothesize that XLMR might be capturing certain features that can generalize well to other languages, such as the complexity of source sentences or the fluency of the target sentences. It is possible that multitask learning works better when language pairs share certain characteristics. Therefore, we investigate whether combining language pairs that share either source or target languages can be more beneficial. For that, we use the MTL model, but with a reduced set of languages. In this table, we compare MTL models trained on language pairs that share the source language against MTL models trained on the same target language. As we can see from the results, the MTL models trained on English source language perform worse than MTL models trained on all language pairs. In contrast, MTL models trained on English target languages perform a little bit better than MTL models trained on all language pairs on 4 out of 5 language pairs. To test whether a multilingual model for QE can generalize beyond language pairs observed during training, we also conduct experiments varying amounts of in-language data. We build and compare base BL and base ML models. We train base BL models only on subsample training data, while we train base ML models on both subsample in-language training data and all language pairs in other languages. We present the results in the table and figure below. As we can see, multilingual models perform better than bilingual models in all training configurations. Moreover, in 3 out of 7 cases, the zero-shot models perform better than the fully trained bilingual models. This provides strong evidence that the QE task can be solved in a multilingual way without loss of performance compared to bilingual models. It also shows strong evidence for the zero-shot applicability of our models. Having pre-trained representations can help to build state-of-the-art multilingual systems. However, these representations are costly to compute in practice, which limits their applicability for building QE systems for real-time scenarios. Now, we switch to test whether Glassbox approach can generalize across different languages. Glassbox approaches to QE extract information from the neural MT system itself to predict quality, without relying on any external resources on the source or target sentences. We used 5 best performing Glassbox indicators from previous work. The average neural MT log probability of the translated sentence, the variance of word level log probabilities, the entropy of neural MT softmax output distribution, the neural MT log probability of translations generated with Monte Carlo dropout, the lexical similarity between MT hypothesis generated with Monte Carlo dropout. We trained an XGBoost regression model to combine these features. I will now share some result analysis of the Glassbox QE model. From the table below, we observe a smaller performance degradation when testing on different language pairs. For all language pairs except English-German, we observe a relatively small decrease in performance of up to 0.09 when training and test language pairs are different. This suggests that the indicators extracted from the neural MT models are more comparable across languages than input features from pre-trained representations. Comparing to the Blackbox QE results, we do not see any gains in performance from training with all available data. The reason could be that training a regression model with a smaller number of features does not require large amount of training data as compared to large neural model. We also observe that similar to the Blackbox results, English-German benefits from using data from other language pairs for training. This might be partially due to the distribution of DA scores. To better understand these results, we look at the distribution of the DA scores and the distribution of the neural MT log probabilities. From these figures, while log probability distributions are comparable across language pairs, the distributions of DA scores are very different. This suggests that the decrease in performance when testing on different language is related to a higher extent to the shift in the output distribution across languages than to the shift in the input features. I will end the presentation with some conclusions of this work. We explore the use of multilingual contextual representations to build state-of-the-art multilingual QE models. For Blackbox approach, we observe that multilingual QE models are always better than bilingual QE models. Having multitask models that share parts of the model across languages and specialize others does not necessarily yield better results. Multilingual systems for QE generalize well across languages and are powerful even in zero-shot scenarios. For Glassbox approach, we observe that Glassbox features are comparable across languages, but training multilingual systems with them provides little value. The distribution of the output labels matters for the evaluation of QE. I have come to the end of my presentation. Thank you for listening.